but we'll be doing some standard level acids as well. We spoke a bit about strong acids and alkalis yesterday. I'm just going to recap a couple of things from that you weren't super secure on. What you were secure on is the definition of pH as being minus the log of the hydrogen ion concentration. And it's worth, at this point, highlighting that you can have minus the log of the hydroxide ion concentration as well, and that's POH. Okay. So there's those two things that we talked a bit about yesterday. You need to be comfortable, though, what an acid is, a strong acid and a weak acid. And I just want you to talk through that for a second, please. So good. So your definitions of acid are good, strong acid, and weak acid. And I'm just going to make a note here. I'm not going to write this down for time reasons. Definitions of strong and weak acids, you're pretty secure at. So I'm just going to remind you of as a thing you've got to be comfortable with. The thing I was just checking there is about the kind of different theories of acids and bases that you've covered. And so it looks like you've covered, it's a while since I've taught this, I'm just double checking. You've got, this is the Bronsted-Lowry definitions, that term familiar to you, Bronsted-Lowry or Arrhenius definitions. You've also learned about Lewis acids, of course, which are acceptors of electron pairs. There's different definitions of acid. We're talking about Bronsted-Lowry specifically there. Okay? All right. So if you're, very briefly, a couple of calculations then. If you've got a strong acid, it will fully dissociate. And let's use HCl as an example. If we've got HCl, we've got a concentration of HCl of, say, 2 moles per decimeter cubed, then we can say that the pH is equal to minus log of the hydrogen ion concentration. We can work out that hydrogen ion concentration because the concentration of HCl is equal to the concentration of H+. Okay? And that's because HCl fully dissociates to H+ and Cl-. So however much HCl is in the pot, that's how much H+ will end up in the pot. So whatever the concentration of you got on your bottle there is that concentration. Plug the numbers in, you end up with a pH of, as you learned yesterday, that comes to minus 0.30, I think, from memory. Was that right from yesterday? And what surprised one or two of you is that you can get minus pHs. So it's literally just the minus the log of the hydrogen ion concentration. So you plug that number in, and that's what you get. It tends to be, and the reason we teach year 7s this, that the pH tends to go from about 1 up to about 14. But that isn't, they're not limits, they're not boundaries. You're limited by the chemistry rather than the numbers, all right? Anyway, so if you've got a different example, if you've got H2SO4, we've got to remember that that's a diprotic acid, and we'll release 2 hydrogen ions per acid to give 2 hydrogen ions and sulfates. If you've got, for example, sulfuric acid, which is 0.5 mole per litre, the hydrogen ion concentration is therefore 1 mole per litre. And so in your heads then, what's the pH, without doing it in a calculator, what's the pH of that stuff? So you're right, the pH therefore is equal to 0. If you were to dilute this by 1,000 times, so if you dilute this acid by 1,000 times, by adding lots of water, what would the pH be now without using a calculator? So if you dilute it 10 times, the pH goes up by 1. If you dilute it 100 times, the pH goes up by 2. Dilute it 1,000 times, the pH goes up by 3. So the pH would be 3. So that's reiterating to you the purpose of this logarithmic scale. The pH increases by 3 to 3, right? So there we go. So just making it clear what our logarithmic scale is there. All right, so we've done a little bit on strong acids. That's all I'm going to do. We're going to talk about strong bases now, and I'm going to remind you that to work out, and you were kind of all right at this yesterday, so I'm not going to spend long on it, but you need to know and be comfortable with this idea of Kw, which is equal to the concentration of hydrogen ions and hydroxide ions in an aqueous solution. And at standard conditions, that is equal to 1 times 10 to the minus 14. And the units, if you want to know them. Although we don't worry about units for this, are that, all right? So 1 times 10 to the minus 14. So the pKw, therefore, is 14. If you plug that number into the calculator, you get 14. So we can use that to work out the pH of strong bases. And so if you have a base like sodium hydroxide, for example, and that sodium hydroxide concentration is equal to 0.2 moles per decimeter cubed, and you've got another base, let's say calcium hydroxide, and that's equal to, let's say, 0.25 moles per decimeter cubed. Can you work out, please, the pH in each of those cases? And then we'll walk through it. So 2 methods of doing it. I'm going to do the sodium hydroxide one way. I'm going to do the calcium hydroxide one the other way and pick out the key difference. So one way of doing it is to say, well, we know that Kw is equal to H plus times OH minus, and that's always true in an aqueous solution. And we know that the concentration of the hydroxide ions is equal to the same as the sodium hydroxide, because it's a strong base, fully dissociates to sodium ions and hydroxide ions. And so we just plug the numbers in. So we've got 1 times 10 to the minus 14 equals H plus times 0.2. You rearrange that to make H plus the subject of the equation and do minus the log of that number, and the pH comes out at 13.3. It looks like most of you have got, which is good. And then the other way of doing it is by calculating the pOH. But we've got to be careful here. The thing I was hoping no one would fall for is that the hydroxide ion concentration here is 2 times the calcium hydroxide concentration. I think from looking around, most of you got that, so it's 0.5. So if you do the pOH, what's minus the log of 0.5, please, folks? Which is 0.3, and we can say that pKw is equal to pH plus pOH. So you can do these in your head if you know the pOH. And the pKw is 14. pH is what we're trying to find out, and that's 0.3. So we can say the pH in this case is 13.7. There's a couple of ways of tackling that question, right? So enough of all that stuff. Let's press on to some more demanding stuff and look at weak acids, which, as you said, are acids which only partially dissociate. I surprised some of you yesterday to tell you that the degree of dissociation of weak acids is much, much, much less than you had realised. Right? It's a really surprisingly small amount. And one thing I'm not going to cover today is I'm not going to talk about the reactions of acids. I think you can, you've done that right back from year 9, but things like reacting with carbonate, and reacting with magnesium, reactive metals, and that kind of stuff, and reacting with metal oxides and metal hydroxides. Weak acids behave the same as strong acids, but everything's just a bit slower, okay? So it's just about rate of reaction, because the concentration of hydrogen ions is much, much less than the concentration of the acid you start with. You can work all of this stuff out by using Ka. Ka is the acid dissociation constant, and we can write that as CH3COOH, H plus, and then the acid over there. I will actually talk about conjugate acids and conjugate bases in a minute. It's a really common IB question, so we'll do that too. But we'll start with this one. Now, it's really, really, really important that we spend a moment just thinking about this. So once you've written that, just pop your pen down or catch up in a minute. I really want to press home this point to you. Now, you probably all remember being shown that you can turn this into, and I will show you this shortly myself, we can make a perfectly good assumption that Ka is more or less equal to this. This is what we're going to use to do our calculations. But this is the definition. So if ever you're asked to define Ka, you must give this as an answer. You can't give A minus H plus HA. You give the actual acid that it's actually talking about with its conjugate base and H plus at the top and the acid underneath. And you can say there are assumptions that allow us to work out the pH easily, and you need to know what those assumptions are, but know that they're assumptions rather than the truth. The truth is this thing here. But we make the maths easier, much easier, by making a couple of assumptions. And this equation, by the way, we use later on in the, and this, we might come to this later today or more likely tomorrow. We'll use this again with buffers. And the assumptions we're making with weak acids do not apply to buffers. So this step here applies only to weak acids. So weak acid assumptions. And I want you to think about those for a moment and see if you can tell me what those two assumptions are, or either one of them. That's meant to say assumptions, it's a bit messy. We're going to think about what those two assumptions are that allow us to make that step. Let's talk about that for a moment. The assumption we're making here is this and this are the same. So one of the assumptions is about the numerator, and one of the assumptions is about the denominator. That's how I remember it. Because I always, whenever I teach this, I kind of go, you know what I'm like, I really sort of have the notes out. I have to kind of remember it as I go along. So I know one's about the numerator, one's about the denominator. And you are right that the first assumption, so I'm going to write the assumptions down here, and you need to know these. If you want to really push the top marks, you should know this sort of stuff really well. Okay? So the assumptions are that H plus concentration is equal to the CH3COO minus concentration. And that's very reasonable if you look at the equation at the top. This breaks apart into one of those and one of those, right? But there's another source of H plus in the pot that we're ignoring. The other source of H plus is water. So assume no H plus from dissociation of water. We know that water dissociates, and we wrote down the ionic product of water earlier on, you know, the KW thing. We know that water does dissociate a little bit to give H plus and OH minus, but you should know that in water, neutral water at least, this will dissociate to give you 1 times 10 to the minus 7 moles per litre H plus, which is tiny compared to the amount of H plus and that's released from the acid breaking apart. So it's perfectly reasonable to say that there's no H plus from dissociation of water. Otherwise, you've got to do a little bit of extra maths, and it doesn't change the answer, particularly when you log the final answer. Okay, so that's the first assumption. You should know that. You should be aware of that. The second assumption is to do with the denominator, and this goes back to your knowledge of equilibria. That actually these values here are the equilibrium concentrations. Equilibrium, equilibrium. And we've said, for example, that the acid here is 1 mole per litre. That's the initial concentration before it's dissociated a little bit. And because I told you yesterday that it's only dissociated a tiny amount, and if you think about the Ka being something as small as 1.7 times 10 to the minus 5, as we said yesterday, this number and this number is tiny, this number is relatively big compared to these two numbers at the top, partial dissociation. This number, this acid, I'm going to write it out slightly differently, has barely dissociated, which means that the concentration at equilibrium is almost exactly the same as the concentration at the start. In other words, it's 99.999 still this stuff. Otherwise, you've got to do, when you do the maths here, you've got to do this number take away x, and you've got to use the quadratic formula to solve it. Right? So we simplify it by saying the equilibrium concentration is the same as the concentration given in the question, which is the initial concentration. Right? So the assumption, the way that I'd write it out, simply assumption 1 is what I've said there. Assumption 2 is that the CH3COOH concentration initial is equal to the CH3COOH concentration equilibrium. It's barely changed at all because there's only very partial dissociation, very partial dissoc. And I'd say of those two assumptions, the first one is more important and the one you're more likely to be asked about, but it's worth being aware of both. But then the maths is dead simple, and we are not going to spend long on this. And I'm trusting we've done lots of, or will be doing from, say, Smoz Notes, a whole bunch of practice questions for weak acids. But let's do one anyway. So you should know that the answer for weak acid, the answer is going to be in the kind of, most likely in the kind of 2.5 to 6 pH range if it's a weak acid. But let's just pick a weak acid. Let's stick with ethanoic acid, because I know the Ka is 1.7 times 10 to the minus 5. And let's say the concentration of that stuff, or the initial concentration, is 2 moles per decimeter cubed. We can easily work out then the pH of that. Now, if I just write out the equation, plug in the numbers, I'm going to miss out the definition step because I've got it up here, and I'm going to say that the Ka is more or less equal to the hydrogen ion concentration squared over the concentration of the acid we're interested in. And all we have to do is rearrange that now. And forgive me, but I'm going to trust you can do this maths reasonably well, because it's not the first time you've seen this. And if you can't do this rearrangement on the fly in an exam, learn it. That dot there just means multiplied by. And so all we've got to do to work out the hydrogen ion concentration is do 2 times by that number there, the 2 which is the concentration of that number there is the Ka, so that will be 3.4 times 10 to the minus 5. We square root that, and then we go work out the pH from there. And if someone could just quickly tap that into a calculator for me, that'd be lovely. Well, so we end up with the hydrogen ion concentration, thank you everyone, as that, which if you do minus the log of that, you get 2.23. So that's a fairly low pH weak acid. I've got a bunch of practice questions, you can do more of these later on, okay? But let us move on to weak bases then, because, and I've got a whole load of questions on this as well, but we're just going to talk about a general base as being B, and bases are things that can accept hydrogen ion, so we really need to include water in this expression, in this equation. I find that people struggle, personally I remember being taught weak bases and finding it much harder, and I found that teaching it, people tend to find it harder as well. So if I were you, I'd be spending more time on this if you've secured the weak acids stuff. And we can say for a weak base, it's exactly the same though, really. I don't know why it's any harder, although I know I found it harder. But Kb is equal to BH plus times OH minus divided by B. Now, because water here is the solvent, and therefore the concentration doesn't change in the course of this reaction, we just don't bother including, we don't include water into the Kb expression. That's absolutely normal, and you've seen that in the equilibria topic. So we don't include water if it's the solvent in this. Okay, so that should be relatively straightforward. And an example of this might be quite a quick example. There's an example here. We're going to use ammonia, which is a base we're familiar with, and the Kb of ammonia is 1.78 times 10 to the minus 5, and we can make the same assumptions as before. It's exactly the same approach. So we can say, if we're using ammonia as an example, I'll write out the equation. NH3 plus water goes to NH4 plus ammonium, that is, and hydroxide. We can say that Kb is equal to the hydroxide ion concentration times the ammonium concentration over NH3. That's what it's equal to, but we can say that's roughly equal to the hydroxide ion concentration squared over the ammonia concentration. Exactly the same as the weak acid stuff. So I don't know why as a student I found it any harder. I don't know why you would either, but typically we practice it less, I suppose. You plug those numbers in after you've done the rearrangement like last time. So it's exactly the same process. The hydroxide ion concentration is equal to the square root of Kb times the concentration of NH3. Let's say this time the concentration of NH3 is equal to 1, just to make it easy. You should be able to work out the hydroxyl ion concentration, and from that, either using POH or using KW, you can work out POH. So if someone could help me out with the numbers, I'll write them down. So you can work this out either way. You can work it out as the hydroxyl ion concentration is as given, it's 4.22 times 10 to the minus 3, and then work it out from KW from POH gives you that answer. Thumbs up, everyone getting the same things as each other? Right, lovely. Okay, so that's as much as I'm going to do on that, but this is where I'm going to hurt your heads a little bit. And I want you to be cut. This is fairly sort of moderately complex stuff, but you're expected to know that Ka times Kb is equal to Kw. And I'm going to talk about Kw a little bit as well. So, right, so I want you to think about what this means. So if we've got a weak acid, and I'm going to use a generic, sort of general example, and I hope that's okay, and you'll see this in questions, but if you've got a weak acid, it can break apart to give it a conjugate base and H+, right? And we can say the Ka for that is equal to H+ times A- over HA. And I've got this on some slides which I'll share with you as well, by the way. People often find this kind of tricky. Right, now this here, this A-, what's the other thing we can call this? So this is the acid, so what's this therefore, please? So A is a A is a base, A is a conjugate base. And when we talk about the pH of salts, that's going to be important later on. So if you've got a salt, I'll come back to that later, I'm waffling. So therefore, that A-, if it's a base, can react with water. It's a weak base, it's not going to react very, it's not an equilibrium that's going to be very far to the right, but you can have this going on. Okay, so that A- can behave as a base and therefore will have a Kb. So for every acid you've got HA, which has got a Ka, you will have a conjugate base which has got a Kb, coming from its reaction with water. And that Kb can be written out as we did before. And so we've got OH HA over A-. Right, so somebody somewhere decided, I know, for whatever reason, I'm going to multiply those two numbers together and see what we end up with. So we're going to take this, we're going to multiply it to that, and then see what we end up with. So Ka times Kb is equal to, I'm just going to write out those equations next to each other, H+ times A- over HA times by OH- times HA over A-. So I've just written those two things out next to each other, and kind of GCSE or sub-GCSE maths means, have I made a mistake? A little mistake there, sorry, thank you. There's no minus there, obviously. GCSE kind of level maths here is we can simply say, well, whatever that number is, it's the same as that number, because it's just the concentration of HA. That can be cancelled out with that, and we're left with H+ times OH-, which is equal to the Kw. Hooray. So Ka times Kb is equal to the Kw. And what you end up with is you can work out the Kb of an acid for which you've been given a Ka. I'll say that again because I think I said it quite right. you can work out the Kb of a conjugate base if you know the Ka of its acid. Yeah, that's what this is allowing you to do. So if you've got, let's say that you've got ethanoic acid and it's got a Ka of 1.7 times 10 to the minus 5, we can say the Kb of the ethanoate ion can be worked out from that. Okay, that's what I'm getting at there. And I'm not going to work through an example there. Hopefully that's clear enough. All right. I do want to just talk a little bit about Ka, Kb. I'm going to stick with Ka, but all this applies to Kb as well. So if the Ka increases, what does that tell you about the strength of the weak acid? So we know weak acid will have a tiny number, but if I make that number bigger, what's happened to the strength of the acid? Is it increased or decreased? Perfect. Yeah, so if you've got an increase in Ka, it means your numerator, which are the products, has increased, which means it's dissociated a bit more. And so if you've got a bigger Ka, you've got a stronger acid, and that should be like really secure and available in your exam to be able to sort of recognise the strength of acids based on their Ka. What's a little harder is, what about the pKa? If the pKa increases, what does it tell you about the strength of an acid? Around, yeah, good. So if you've got a bigger Ka, you've got a stronger, still weak acid. And if you've got an increase in pKa, you've got a weaker weak acid. So they're opposing each other. I think it's minus the logarithm. If you just play around with the numbers in the calculator for a bit, which, being the sort of strange geeky fellow I was and am, I would have done that at one point just to convince myself that pKa and Ka are kind of going in opposite directions. Let's talk about Kw a little bit, and I'm feeling I've talked about this with you before. Kw is equal to 1 times 10 to the minus 14, and that's given in your data book, but that assumes standard conditions. What happens to the Kw if I increase the temperature? And the only clue I'll give you is that reaction as written there. Is that endothermic or exothermic? Is breaking that bond there endothermic or exothermic? So if that's endothermic, because it's breaking a bond, if I increase the temperature, is that equilibrium going to shift to the left or to the right? If I increase the temperature of an endothermic reaction, where will Le Chatelier's principle say the equilibrium shifts? Yeah, the equilibrium will shift to the right if you increase the temperature. And if you increase the temperature, equilibrium shifts to the right-hand side. So Kw will therefore increase because you're going to have more H plus and OH minus. So the Kw increases. Okay? So we get the Ka is not a static number. It's just like any equilibrium constant. It's only affected by temperature, but it is affected by temperature. You need to understand how and why, and therefore pKw changes, and so does pH and pOH. So if we're at 70 degrees, say, the hydrogen ion concentration is not going to be 1 times 10 to the minus 7. It's going to be a bigger number. I wonder if you know how to work that out. So let's say I don't have the numbers here, so forgive me, I'm just going to make up a number. It could be completely random. So if you increase the Kw, let's say it increases by a bit. I just don't know what it would be, but let's say for argument's sake, we increase the temperature, the Kw goes up to 5 times 10 to the minus 14. I don't know what temperature that would be, but just a number that's a bit bigger, right? So what will the hydrogen ion concentration be if the Kw has gone up because I've increased the temperature? Work that out, please. Or do you know how to work that out? I wonder if you do. So now, if that's true, and water breaks apart to give H plus and OH minus in equal concentrations, it must therefore be true that in neutral water, the hydrogen ion and hydroxyl ion concentration are the same, so you can say that Kw is equal to H plus squared. So to work out the hydrogen ion concentration, you've got to do the square root of that number. So the hydrogen ion concentration is the square root of 5 times 10 to the minus 14 at this random temperature that I've made up. What does that come to, please? 2.2 to to the minus 7. So what is the pH of water at that new higher temperature, please? So minus the log of that number there, it will be 7 and a bit, right? 6 and a bit. 6.65, yeah, 6.65. So pH of water has decreased at high temperature. So water is acidic at high temperatures, right? Or wrong? No, why not, Jermaine? Good. You've still got, so even though pH has gone down, that's the new neutral pH at different temperatures. So pH 7 being neutral is only true at 25 degrees C. Right? It's a misconception that we drill into year 7s and have to unpick in year 13. So pH neutral is 7. If you've got that and that being the same, which is true at 25 degrees C, but pH changes ever so slightly at higher temperatures and lower temperatures, changes. Alrighty. We'll start by looking at pH curves next, and what's happening in the pH curve. It will be a little bit of a precursor to the buffers bit, which is the thing you will all spend time on. There's no point spending time on buffers unless you understand the rest of it. So you've got to be able to draw potentially any pH curve. Strong acid, strong alkali, either way round. Weak acid, strong alkali, either way round. Strong alkali, weak acid, either way round. Weak acid, weak base, either way round. Okay? So you've got to be comfortable with all of those. And we're going to sketch 4 of them now and just make sure we're comfortable with them. You have to invert them if you needed to. But what's happening at each stage in your standard pH curve? That's a pretty ropey curve, forgive me. But be comfortable with here that you've got pH on this axis, and you've got the volume of your, e.g. sodium hydroxide, your strong alkali over here. So volume of alkali there. And so let's say this is strong acid and strong alkali, so we'll use HCl plus NaOH. What's going on at each of those stages? And I'm going to label those stages A and B and C. It's kind of the important points of this curve. So A is, of course, only acid. Nothing's been added to it. Now, I think what often confuses people is that I think B is kind of halfway through the reaction. But B is not halfway through the reaction. B is at the reaction, when the reaction is completed. B is what we call the equivalence point. And that's when you've added equal quantities of HCl and NaOH. When I say quantities, I mean number of moles. So they've completely neutralized each other. So the only things that are present there, apart from the water solvent, is only NaCl. And in obviously the bit between A and B, you've got some remaining HCl and a bit of NaCl. But at B, all of it's been used up. And at C, up here, now we've got excess sodium hydroxide being added. So at C, we've got NaCl, it's left over from the reaction, plus we've got NaOH excess. Because when you do a titration, you shoot way past the equivalence point in order that you can see that nice vertical region where neutralization has taken place, right? And for a strong acid, strong alkali, the pH at that point is going to be equal to 7, right? And that's because the pH of equivalence point, let's write it that way, equals 7, because pH of sodium chloride solution is equal to 7, right? Sodium chloride is a neutral salt. So any salt that's made from strong acid, strong alkali, will have a pH of 7. Okay, and I'm not going to talk about indicators in this session, I don't think. I did share with you yesterday a little video last night about indicators, which if you want to look at, you can do, but I might just blow past that and we'll talk about other things. But you can use an indicator which has got, I can't remember what it is in your current data books, but a P-in or a pKa for that indicator is close to matching the equivalent, the pH of equivalence point as possible. So another curve we should spend time on is when we've got a weak acid and then we're adding to it a strong alkali. So this might be something like CH3COOH again, plus NaOH, and we're going to end up with sodium methanoate, and water. Okay, so just as before, at A we've got only acid, of course, and the pH there would be about 3 for argument's sake, pH 3. And up here, just like before, we've got the salt, which is CH3COONA, and some excess sodium hydroxide. So that's going to be pH 14 up there, because we just dumped in a load of excess sodium hydroxide in there. This time I'm going to highlight this region here. I'm just going to label it for now as the buffer region. And we'll learn next lesson that buffers are regions where addition of small quantities of acid or alkali cause minimal change to pH. But we'll talk about that another time. But here is the equivalence point. And at that equivalence point now, we've completely added enough sodium hydroxide to neutralize or to react with all of the ethanoic acid. So all that we've got is present there, apart from the solvent water, is CH3COONA+. And you've got to be really comfortable with the concept, the idea, the pH of the equivalence point is not 7 for a weak acid strong base. In fact, it's above 7. So the pH, we're not going to give you a number here, but its pH is greater than 7. And there's two ways of thinking of this. There's a simple way, there's a more complex way, and I'd like you to be able to do both. There's a simple way to give you that security in an exam, and a more complex way to answer any questions on it. The easy way to think about it is like a tug of war. Weak acid, strong alkali, who's going to win the tug of war? Right? You've got both present. You fight that, they're kind of fighting each other, if you like. It's a bit of a silly way of thinking about it, but the strong alkali will win, and the pH is going to be affected more by the sodium hydroxide. It's a kind of a simplistic and not really accurate way of thinking about it, but it helps me remember that I've got it right here. The strong alkali, weak acid, pH greater than 7 when you've neutralized everything. But that's not the explanation. The only time you've got pH greater than 7 is when you've got a slightly higher concentration of hydroxide ions than hydrogen ions. So there has to be an explanation which involves that. And this is usually poorly understood and certainly poorly answered in exams. You've got to be able to justify the presence of hydroxide ions that are not from the dissociation of water. And that comes from the conjugate base that we've just generated there, reacting with water, and it's a weak base, it's only partial reaction, but that generates a little bit of that stuff, and I've always got a bit confused about this as a student. Some of you go, well, that's an acid, but it's a weak acid. The key thing though is you generate hydroxide ions, and you know, don't you, that the presence of hydroxide ions is what defines POH and therefore pH. So by having the salt of the conjugate base in there, you generate hydroxide ions, and so the pH is greater than 7. pH is therefore greater than 7. Right. I'm not going to do the equivalent weak base strong acid curve because the arguments are exactly the same but just reversed, so forgive me. I think that is in one of the videos I've given you, but plus notes and stuff that I'm going to share with you. But I do just want to do a couple of quick questions around conjugate acid, conjugate base. So I want you to tell me the conjugate base on your mini whiteboards, a little bit of mini whiteboard stuff. So I'll pause the video and we'll do a few of these together. What's the conjugate base of that stuff? So the conjugate base, when this deprotonates, it does so twice, and it does so. So the conjugate base is actually this stuff. That stuff can also deprotonate to give you H plus and SO4 2-. So the conjugate base of sulfuric acid is HSO4-. The conjugate base of HSO4- is that stuff. This stuff is an acid, which is why it's behaving like an acid there, but it's also a base. Okay, so got this idea of, I'm not going to talk about amphiprotic and amphoteric, but today at least there's that. What would be the conjugate base of hydroxide? I've seen this in the paper. It's a bit of a weird one. What's the conjugate base, the theoretical conjugate base of that stuff? You're struggling with this. All you've got to do is take away H plus every time. Good. Yeah, it looks weird, doesn't it? Because that doesn't really happen. But that stuff, all you've got to do is take away H plus. What's the conjugate base? This is a weird one. You won't see this very often. What's the conjugate base of ammonia? Yeah, it is. Yeah, good. It's a skill that's dead easy. It's worth spending a moment or two on. I hope that was useful. We'll leave it there, and we'll do buffers next time.